right, so before we get going, you might be wondering, all right, what exactly is the Neil Gehrels Swift mission? The answer is that it's a mission that studies the birth pangs of black holes. Into the 1960s, we were in the middle of a Cold War with the Soviet Union, and we signed a treaty to ban the tests of nuclear weapons. Now, Russia's a big place, and so it would have been very easy for the Soviets to break that treaty. So what we did was we launched this series of satellites called Vela, which were equipped with gamma ray detectors. Gamma rays are the highest energy form of light, and they are only emitted by nuclear processes or incredible hulks. So if we saw a flash of gamma rays from the Soviet Union, and we knew that Bruce Banner was nowhere in the area, we would know that they had broken the treaty. Well, in the 1960s, they began to detect flashes of gamma rays, but not from the Earth, but from space. Now, this was restricted information, so it was years before it was published. But that set off a decades-long crusade to try to figure out what these gamma ray flashes were coming from. They were sudden bursts of gamma rays, and because they are the highest energy form of light, they had to come from something incredibly energetic. Most people thought it had to be something nearby, because if something was millions of light years away producing this kind of energy, it would have an unimaginable explosive force. Year after year, we got closer and closer, and in the 90s, thanks to the Beposat satellite and ground-based observers, we identified the first optical counterpart and figured out a little bit of what these things were, and that's the origin of the Swift mission. These gamma ray bursts don't last long. The first time anyone was followed up was 6 years after the fact. Even with later satellites, it took hours to follow them up at best. So Swift was designed to follow these things up quickly. That's why it's called Swift. It's a fast-moving spacecraft that has 3 instruments on board. One is the Burst Alert Telescope, the BAT. This scans a large part of the sky looking for flashes of gamma rays. And it uses what we call a coded mask aperture array, where it has a mask on the front where the gamma rays come in, they go through the holes in the mask, they create a pattern on the detector, and because we know the code in the mask, we deconvolve that to get a very good position for the gamma ray burst. Once that's detected, the spacecraft automatically repoints itself, pushing over through the sky, dropping whatever it's doing, and repositioning to get the narrow field instruments, the XRT, the X-ray telescope that uses grazing incident optics to focus X-rays, and the ultraviolet optical telescope, a more traditional telescope that is a copy of the optical monitor on the XMM mission. These are narrow field instruments, so they get down to where that gamma ray burst is very precisely. We send out alerts to the community, and then they can be studied by other telescopes. Thanks to these, we have learned that gamma ray bursts are the birth pangs of black holes. There are 2 kinds of these. There's the long gamma ray burst, which is anything 2 seconds or longer, where you have a massive star that goes off in a supernova eruption. And when it does, it compresses down, leaving a black hole behind. And as it does, it shoots out this jet of material from its north and south poles. And if they're pointed at that, we will see a gamma ray burst. That's what's giving off the gamma rays. Or it's a short gamma ray burst, less than 2 seconds, where you have 2 neutron stars, these shriveled husks of dead stars, merging together to form a black hole. And they give off a very brief but intense flash of gamma ray radiation. This is what we do. This is our bread and butter. We have discovered, as of this point, over 1,700 gamma ray bursts that we have studied at various points. And we go off, we detect them, Swift slews to them, usually within a couple of minutes. It sends out text messages to us. It wakes us up, usually in the middle of the night. We jump to our computers, we look at the data, we send out notices to the community, other people look at it. And we've been doing that for 20 years. But the other thing about Swift is if you build it, they will come. If you build a telescope that can get simultaneous X-ray, UV, and optical data, that can respond on short notice, that can hit a target over and over again if it needs to, people will find things to do with it. So there was a lot that Swift does now that wasn't in our original programming. We look at comets. We look at galaxies. We look at a lot of supernovae. We look at active galaxies. We look at black holes. We look at near stars. We look at all kinds of things. If it exists in the cosmos, we have probably looked at it. The only thing we haven't looked at is the planets and the sun, because they're literally too bright. So that's what we've been doing for 20 years. We're still learning a lot about gamma ray bursts, and we're especially learning a lot about other science. You're going to hear a little bit about that in the video that I've just finished editing, actually. I'm recording this a couple weeks after my shift as ODS. You might be wondering where the Neil Gehrels comes from. Neil was the original PI of our program. He was the heart and soul of the Swift program for many years. He unfortunately passed away a few years ago, and NASA decided to name the telescope after him, not only for Swift, but for the contributions he had made to high energy science throughout his career. And so that's where our name comes from. So you're about to see basically a week in the life of this exciting space mission, now 20 years and going strong. So I hope you'll enjoy it. All right, it is 8:30 in the morning. It is about half an hour before things get rolling here at the Swift mission. Actually, some people are already here. The flight ops team, our engineers, are already here doing some checking up on the spacecraft and some usual health and safety stuff. So, but everything gets rolling for the ODSs and the science team in about half an hour with what we call the daily planning meeting. So I'm going to walk you through that and what a typical day starts like for Swift with this planning meeting. So what we do is we all get on a telecon, and what it consists of is a series of reports from people who are on call who have various duties regarding the spacecraft. There's a bewildering variety of acronyms and initialisms connected with Swift, so I'll try to walk you through them. So you start out with the report from the Observatory Duty Scientist. That's the role that I will be taking over in half an hour, and the role of the ODS is to manage the science of the spacecraft. We take in TO requests as they are made. We correspond with scientists who are getting data from the spacecraft. We send out notices to the community of whatever's going on with the spacecraft. If we need to do uploads, we manage that. And so we report in the morning on what has gone on in the last 24 hours, whether we've had bursts, whether we've had TO requests, and so forth, that everyone needs to know about what's going on scientifically. After that, we will get the report from the flight ops team, the FOT. These are the engineers, Penn State engineers, who do the running of the physical operations of the spacecraft. We do the science side, they do the operations side. So they'll report on anything that's been going on with the spacecraft, whether they send commands to it, when we have to get the plan onto the spacecraft, whether we have problems with our ground stations or problems with anything on the spacecraft that they had to deal with, they'll report on those. You then have reports from the 3 duty scientists, the Burst Alert Telescope Duty Scientist, BDS, the X-ray Telescope Duty Scientist, the XDS, and the UVOT Ultraviolet Optical Telescope Duty Scientist, UDS. And they will report on how those instruments are functioning. Usually, and so if we sent commands, if we had an error, if they went into the safe mode or something like that, they'll report on that and what's going on. Usually those reports will consist of bad is fine or UVOT is fine. But if something has gone on, let's say UVOT safed itself because it slewed over a bright star, we'll report on that and what happened and when we recovered it. After that, you will have a report from the science planners. These are people with at least bachelor's degrees in physics or astronomy who do the actual planning of what the spacecraft is going to observe. During the day, we are observing dozens and dozens of targets, sometimes over 100 targets, and they're all over the sky. Swift orbits the Earth every 96 minutes. We have various constraints. We can't point too close to the sun or the Earth or the moon, and so they are planning the targets, this path that Swift is going to go through the sky to follow all the targets and try to get as much science as we can given our constraints. And so that's a very intense job, but they do a really good job of optimizing what the spacecraft can do within the constraints of the physical operations of the spacecraft and what we have going on in space. Then we have a report on any gamma ray bursts we're following. Each gamma ray burst is assigned a burst advocate. That is the scientist who leads the investigation into that burst. And if we end up publishing a paper, we'll be leading usually that part of it, writing and publishing the paper. And they'll report, this burst went off, this is what the duration was, this was how bright it was. And as we're following it up, this is how faint it is getting. This is how we project how faint it's going. And they will advocate on whether we should continue to follow that burst, observing it every day with Swift, or whether it's gotten too faint and is not worth following up anymore. You also have connected with that the BBS, XBS, and UBS, the Burst Alert Telescope Burst Scientist, X-ray Telescope Burst Scientist, Ultraviolet Burst Scientist. And what they do is they put the make the data of each instrument available to the BA, so they have everything at their fingertips. So they know this is what BATCH saw, this is what the XRT saw, this is what the UVOT saw. So they have all that in front of them. Then after that, we will go through our Target of Opportunity, TOO requests. These are requests of which we get, probably we're on pace for over 2,000 this year of targets that people think we should observe, some of which are urgent, some of which are not terribly urgent, but we get all those requests in and we discuss them, decide when they're going to go into the plan or whether we're going to do uploads to do them, and so on. And then we put together the plan for the next day. And that sounds like a lot of people, but it really isn't, because a lot of us wear many hats. After this morning's planning meeting, at 10 a.m. we will switch. We'll do a shift change where the people who were on duty before will go out and a new group of people will come in. And a lot of us wear multiple hats. I will be ODS, Observatory Duty Scientist, so I'll be interacting with the scientists and managing the science of the spacecraft. I will also be UDS, so Ultraviolet Optical Telescope Duty Scientist, so I'll be monitoring the performance of UVOT. And I actually caught a burst last week, so I'll be giving reports as UBS, Ultraviolet Burst Scientist, on one of the bursts we had because it had a optical counterpart. And in order to keep people from being burned out, we rotate those duties around between our institutions here in the US, UK, and Italy. And so that keeps, and each institution for some of the duties will rotate those among a small group of people, so no one gets burned out. They're not on call every single day. Even as ODS or UDS, I'm only on call for a week, and then I go off and somebody else takes over. And I have a few weeks of downtime to do my own science and catch up on sleep and stuff like that. So the rotation keeps everyone fresh and keeps everyone busy. One of the unique things about Swift is that most missions plan out their observations kind of pretty far in advance. We plan out our observations on a pretty short time scale because we are in a time domain. We respond to urgent requests. So today is Tuesday. On Tuesday, we will finalize the plan for Wednesday's observations, upload that to the spacecraft, and begin planning Thursday. Tomorrow is Wednesday. We will finalize the plan for Thursday, upload to the spacecraft, start planning out Friday and Saturday. On Thursday, we will finalize the Friday-Saturday plan, start planning out Sunday and Monday. On Friday, we will finalize the Sunday-Monday plan, start planning out Tuesday. And then on Monday, we finalize the Tuesday plan, start planning out Wednesday. So we're usually only a day or two in advance of the spacecraft in terms of what we plan. But we've automated a lot of this. When I came here a few years ago, we had a big effort to make this stuff as easy as possible to do within the constraints we have. It's still not very easy, but it's a lot easier than it used to be. And that keeps us on our toes so that we can, if a TO request comes in on Monday, we discuss it on Tuesday, we can add it to the plan, get it observed on Wednesday. And that's excluding, as you will see later in the week, when I do uploads directly to the spacecraft for something that's particularly urgent. So I've got 20 minutes left now. I need to get some caffeine in me before my shift starts. But here we go. Start of my shift, start of the week. Let's get going. All right, so it is Tuesday night, approximately 10:15 in the PM. So far, it's been a relatively uneventful day. We never want to say that too loud because the spacecraft might hear us. But before I settle in for the night and watch some YouTube videos or whatever, there are things I need to do. So let's look at what's on the agenda right now. So we have, everything is web-based these days with the mission. So one of the things that we most often do are what we call target of opportunity requests, TOO requests. And people can put in a request on our webpage to observe some target. They have a justification. They describe the observations they want to do. And so far, we have had today 3 TO requests. None of these are particularly urgent, so I'll wait until one of our PIs or acting PIs looks at the request and decides whether we are going to observe it or not. So those can wait. If one of those came in as high urgency, a supernova just exploded or something like that, then I would be planning to send a command to the spacecraft to observe it, but we're not there right now. So we're good with that. Checking on my instrument, as I said, I am on call for the UVOT instrument. I've gotten a couple of warnings about high count rates on the DPU. With the UVOT, onboard electronics are processing data as it gets from there, and if we have something very bright in the field that's producing a lot of photons, a lot of counts, sometimes the DPU will get behind or will have a very high rate. So it lets me know that that's happening. In these cases, it's not anything to be alarmed about. It just means it's a little backed up, so I can ignore those. The science planner today finalized the plan for Thursday, and tomorrow we're going to upload it to the spacecraft. Because of the way the passes are organized during the day, they will have to upload it first thing in the morning. So right now he wants us to make sure everything is good with the Thursday plan. So he sends out the plan. People check the modes for the X-ray telescope, whether it's observing in photon counting or window timing mode, to make sure that those are correct for the science we're doing. The UVOT instrument scientist checks to make sure that the UVOT modes are correct. We have these patterns of filters we use to observe things, so they're making sure those are all safe and that they're all good. Those checks have been made, so now he wants me to do the ODS checks, which are my specific bailiwick. So I'll go ahead and log in remotely to my computer on campus. So what the ODS needs to do are 2 things. One, confirm that the compiled plan is on the right computer so it can be transferred to the spacecraft. So I run a Python script to check on that and make sure that that plan has been transferred. I probably will mention this elsewhere in the video, but I go ahead and mention it now. One of the things we do with Swift is, and other missions do this too, is we, instead of having dates, we have day of year. So it starts with 1 on January 1st and goes through 365 or 366 on December 31st. It has the advantage that it's very simple to use and means that things are very easy to organize. It has the disadvantage that after January, it's kind of unclear what the day of the year is, so I have to look it up. Looks like the plan transferred just fine. And now what I do is I check the reaction wheels. So Swift doesn't have any fuel, so the way it points is it has these flywheels inside, and the flywheels are spinning, and then you slow down the flywheel or accelerate the flywheel, momentum balances and the spacecraft slews in response. So you have this flywheel here, you slow it down, the spacecraft moves, you speed it up, the spacecraft moves the other way. And but these flywheels have a sort of maximum torque they can have that's safe, and so what our planning software does is it predicts what those flywheels are going to do. I check to make sure they're all within limits. They are. Our science planners are very skilled, so we're good there. And now I just email the science planner. ODS checks are good, and we're ready to go. Now there is one final duty today. One of the things Swift does most often is coordinating with other missions to do observations. A lot of the times, if someone's doing, say, an optical observation of a galaxy, they want X-ray and UV data to be taken simultaneously with it so they can look at variations, how the galaxy is changing over time. When we are coordinating with another observatory, first of all, it's usually easier for them to set their plan and then us to coordinate with them, because we only plan a couple days in advance. They're usually planning a week or more in advance. So it's easier for them to set their schedule and then for us to figure out how to work that into ours. And those are higher priority arrangements. Anytime we are coordinating with another observatory, that is bumped up to the top of the queue of the things we are doing. Not necessarily first, but very high in the priority as we go through the list of targets and start scheduling them. And if we have two targets in conflict, decide which one we're going to observe and which one we're not going to observe. So one of our most fruitful collaborations that we've had for many years now is with the NuSTAR mission. This is an X-ray mission. They do certain kinds of X-ray observations. They like to coordinate with us so we get X-ray and UV data at the same time. They do galaxy surveys. They look at explodey things. They do all kinds of science. And what they do is they send us a schedule once a week and say, this is what we're doing this week. And we see if we can coordinate it with. So earlier today, I got that schedule. And so I'm looking at it. All right, so we just have a nice script. I run it. It puts all those observations in the calendar. Now when the science planners go there, there's observations will be there. So I just let the NuSTAR team know. And boom, done. And I just got the approval for, while we were recording this, I just got the approval for one of the targets that we had a TO request on. It's been approved, so I'll walk you through that process. I can't show you my screen because I'm not sure what parts of this are limited and so forth, but so we've approved their requested time. I start putting in all kinds of things. I assign it a merit so that, again, if we have, our schedule tends to get very full. And so if we have a conflict between different priority, different targets, we can observe one but not both, then this will tell the science planners which one to prioritize. Let's see. Then we have observed this one before, so I will assign it an old target ID that will tell the science planners what to use, tell them what to look for. And then we had one visit of a certain exposure time. Put those in. We can change that exposure time depending on what the PI approves. If they say, well, we don't need that much time, let's do less time, we can put that in. Now I put in the modes for the various instruments to use. Add it to the calendar. Boom, done. Different ODSs do things different ways. I tend to not send out the email telling them we have granted you time on the telescope until after our morning planning meeting, just in case someone at the planning meeting says, oh my God, don't observe this, it's a terrible target, which never happens, but it's just a creature of habit. A lot of people will send out the emails when it is approved after they put all the data into the thing. And what they'll get is it's a form letter, but it tells them, this is what we have approved. These are the dates we are planning to do it. These are the target IDs you should look for. This is where you should look for the data on the web to download when you're ready. And also a warning that it's swift. Sometimes gamma ray bursts go off. Sometimes gravitational wave events go off. Every assignment, every target we promise to observe comes conditional that when you roll with Swift, you may lose your observations because something exploded elsewhere in the universe and we were distracted by that. We do try to make up observations if we can, but sometimes you just can't do it. It is, the nature of having a mission that works in the time domain. There's a lot going on. Things can change at a moment's notice. I could just approve this plan. I just sent this a plan approval to our science planner. It could go in, we could send it up to the spacecraft, it looks beautiful, and then a gamma ray burst goes off and it all goes to hell. This took a little longer than I expected, mainly because I was explaining everything to you guys. Hopefully I won't speak to you again until the morning. Won't have a midnight burst, but you never know.